This is session D1, Spin and the Stern-Gerlach experiment of 1922. Last lecture, C7, we wrapped up spatial issues, spatial wave functions. Today we begin the discussion of spin, intrinsic spin, angular momentum. This lecture begins the D series of lectures, which focuses on intrinsic spin angular momentum, or spin for short, and spin states. Spin is an intrinsic, built-in, internal property of elementary particles and composite particles independent of their motion in space, their spatial behavior, and their spatial wave functions. Understanding spin is important to properly understand electrons in atomic orbitals, covalent molecular bonds and crystals, ferromagnetic materials like iron, etc. But as important for learning quantum mechanics, spin is mathematically simpler than and quite different from spatial wave functions. Spin reveals additional aspects of quantum reality and the essential structure of quantum mechanics. Spin has its own mysteries and challenges for our understanding. Spin is the springboard for understanding the technological applications of quantum mechanics, such as quantum communication and quantum computing. Spatial problems and wave mechanics are one aspect of quantum mechanics. Spin is the other aspect. We will see that spin states can be described as finite-dimensional abstract vectors, not the continuous functions of spatial coordinates for spatial problems and wave mechanics. Spin states for an electron only have two components and two independent basis states. Operators that operate on electron spin states are 2x2 matrices. So this seems much simpler than spatial wave mechanics with its partial differential equations. Instead of calculus, derivatives, and integrals, we use a small bit of linear algebra. In fact, the smallest bit you can have, 2x2. However, the components of spin state vectors and operators are generally complex numbers. Real numbers, in general, are insufficient. Let's look at a roadmap for the beginning of the D series of lectures. This first lecture, D1, will describe how spin was discovered. Second lecture, D2, will describe two-state systems in quantum mechanics. Lecture D3 will describe electron spin states and various experiments on its spin states. In later lectures, we'll cover entangled states, photon polarization, and the singlet spin state for atomic orbitals. This is a possible time to take a break. The rest of this lecture is on the Stern-Gerlach experiment of 1922. This is a 1922 experiment that showed that neutral silver atoms have a built-in magnetism that behaves in an odd, non-classical way. It was determined that this magnetism could be attributed to individual electrons, and that electrons have a definite amount of angular momentum as an internal property independent of their motion. We will look at the experiment, the result, and the implication, but we're going to leave some of the physics out and some of the physics as optional material at the end of this lecture. This experiment with silver atoms in a non-uniform, inhomogeneous magnetic field was conceived and proposed by German Jewish physical chemist Otto Stern in 1921. So this was after the Bohr model, an old quantum theory, but before wave mechanics, the Schrödinger equation, and Heisenberg's matrix mechanics. Some other physicists said that the classical result was known and that this experiment was not worth doing. Nevertheless, German experimental physicist Walter Gerlach conducted the experiment in Germany in 1922, and the result was a surprise and not classical. Gerlach communicated the surprising result to Niels Bohr on a postcard. He did a drawing on a postcard. Gerlach continued his research and teaching in Nazi-led Germany throughout the war. Stern left Nazi Germany in 1933 and won the Nobel Prize in 1943 for his work after the Stern-Gerlach experiment, and so this Nobel Prize was not shared with Gerlach. Post-World War II, history seems to have given more credit to Stern than to Gerlach, but what if no one had undertaken the experiment and discovered the non-classical result? After all, some other physicists thought it was not worth doing. This is a possible time to take a break. Here is the experiment. On the left, there is an oven that is heated, and inside the oven, solid silver gets evaporated in the oven, so it becomes atoms of silver. And there's a hole in the oven, so some of the silver atoms can leave, and they have a thermal velocity, so they leave with a velocity. They pass through a collimator, so that to the right of the collimator, the silver atoms are moving in close to a straight line. It's never a perfect straight line, but close to a straight line. And we're going to call that direction the y direction. And then the silver atoms pass through the middle of a gap between two magnets. Now I'm showing them as permanent magnets, but actually Gerlach used electromagnets. I'm not going to show that. I'm showing the top magnet as the south pole and the bottom pole piece as the north pole, and I'm showing the top magnet as having a flat surface, and the bottom magnet as having a triangular point. And so the silver atoms are passing through these magnets here on the left. On the right, I'm showing a view looking down the y-axis. So this is not separate hardware. This is just a separate view. North pole magnetic field lines go from the north pole to the south pole. They point straight from the tip to the flat south pole, but they spread out some from the tip to the south pole. The silver atoms pass right through the center, right above the point of the pole. And if there was no magnet, they would continue in a straight line. They would hit this detector. Gerlach's detector was letting them accumulate on a glass slide and then looking at the glass slide. Nowadays, we could have electronic detectors. We are going to define the vertical direction as north, and so the remaining direction is the x direction, which would be out of the page. So silver's evaporated in the oven. Neutral silver atoms, not ions, travel through the collimator in the plus y direction between the magnet pole pieces to the detector. The magnetic field is inhomogeneous, non-uniform. Because our bottom pole piece is triangular, our top pole piece is flat, as we show here. If a silver atom has a magnetic moment, mu, which is a vector, it will be deflected vertically, the z direction, proportional to its magnetic moment component in the z direction, mu sub z. Now, some of you will not be very familiar with magnetism, and that's okay. You don't have to follow everything that I'm going to say about magnetism. You need to believe it, and we need to get to the results, which are interesting and non-classical. But you don't have to follow every equation. So don't worry about it. Don't try to look up every equation and follow it. Hopefully you do know something about magnets. Hopefully you've held a magnet in your hand, two magnets, and you've been taught and maybe seen that the North Pole and the South Pole attract each other, but the North Pole and the North Pole repel each other, and the South Pole and the South Pole repel each other, and that attraction or repulsion is stronger when they're close together and weaker when they're further apart. And that's the basis for magnetism. You might not be familiar with magnetic field lines. What is a magnetic moment? Well, a magnetic moment is like a little tiny magnet. It gets described in terms of mathematical terms and physical terms, but you could think of the silver atom as a little magnet, and it's going through between two magnets, so it might have reason to be attracted to the North Pole or to the South Pole, or be repelled by one or the other. In order to get through this lecture, I have to write some equations and take you through them, but you don't have to follow every equation. The most important thing is that we get to the result and that you understand the experiment in general. You don't have to understand every bit of the physics and every bit of the math. So what does it mean, the magnetic moment component in the z direction, mu sub z? It means, the silver atom, the little magnet of it, could be pointing in any direction. It could be pointing, straight up and down in the z direction, but it doesn't have to. In which case, it could be angled, and only a portion of it is in the z direction. And that portion in the z direction is called the component in the z direction. And then whenever we say magnetic moment, you can think of the little magnet of the silver atom. We will talk more about that throughout the lecture. But the words that I'm going to use will be magnetic moment and component. If that bothers you, think of it as the silver atom little magnet, and whether it's pointing in the z direction or it's tilted. This is a possible time to take a break. Now, beware, different courses and books show the magnets of the Stern-Gerlach experiment differently. So if you are going to look at Wikipedia or you're going to look at some book, it might show the magnets differently. In fact, it probably does. Is one right? Is one wrong? They have their reasons for showing it differently to teach you. Generally, they will all use the z direction as the same as my z direction. But the triangular pole piece with the sharp tip, I used it as the North Pole, but they might use it as the North Pole or the South Pole. And I put it on the bottom, but they could put it on the top or the bottom. And you'll find all four permutations in different books. Don't be frustrated by this. There's sort of a reason, not a very good reason, but a reason. But I want to warn you that if you just look at different articles or different books, they might show it differently, and their formulas might be a little different. The end result and the importance for quantum mechanics are the same, but it is a little frustrating that books show it differently. The flat pole piece might also be shown as C-shaped or rounded, concave away from the triangular pole. It is almost always seemed to be shown as, as if it was a permanent magnet, but as I said, Gerlach used electromagnets. So because of the different orientations, the magnetic field vector could point upward or downward. It could be increasing or decreasing in the plus z direction. Why is there this mess? Well, partly it's because the electron is negatively charged, so we're going to see later that its spin and its magnetic dipole moment have opposite directions, and different sources that are trying to teach you may want to show one or the other as up. They may want to show the magnetic dipole moment as up, or they may want to show the spin as up, and so they make different configurations of the magnets to show what they want to show. In the end, the result is the same, regardless of whether it gets flipped, and the importance to quantum mechanics is the same, but the learning experience is a little different. So it will be difficult and frustrating to compare two sources, even though the physics is inconsistent. I don't know the actual orientation that Gerlach used. I didn't grab his paper and look at it. I'm showing the orientation that I find easiest to follow and remember and explain, hopefully without making any mistakes. My choice is consistent with Professor John S. Townsend and his book, but it's upside down relative to Wikipedia, and it's different than the MIT course 805X. So this is a possible time to take a break. So here's my orientation for the rest of this lecture. Now, between the pole pieces, we can ignore the end effects. The magnetic field between the pole pieces that the beam of silver atoms passes through, it's passing through above the pointed tip. The silver atoms are moving in the plus y direction. The magnetic field at that point is pointed in the plus z direction, as I've shown here. However, the magnitude of the magnetic field is decreasing in the z direction. It's spreading out, so this line is closer to this point here and further here, so the magnetic field is spreading out, which means it's weakening in the plus z direction. That's critical to make this experiment work. So the magnitude of magnetic field B sub z, the component in the z direction, is decreasing in the plus z direction. From classical mechanics, which we will not prove and you don't really need to know, so don't worry about it. And I don't know it very well, and I'm not worried about it. The force on the silver atom, which remember is neutral, the force on the silver atom, the vector force, is the gradient, a vector differential operator, the gradient operating on the vector dot product of the magnetic moment of an individual silver atom dotted with the magnetic field, and in between the pole pieces we can ignore any component from the y direction of magnetic field, which would be at the ends, but we can ignore it in the middle. So it's the gradient of this, the result of the dot product, the z component of magnetic dipole moment times the z component of magnetic field plus the x component of magnetic dipole moment times the x component of the magnetic field. So this is going to lead to a force in the z direction and a force in the x direction, and it turns out we'll be able to ignore the force in the x direction. I'll talk about this more later. And the force in the z direction is what's important to this experiment. And that force, the magnetic moment in the z direction is not changing along the travel of the silver atom. So it's not changing And so we could take it out of the derivative. So the force in the z direction is approximately the z component of magnetic dipole moment times the derivative with respect to z of the z component of the magnetic field. And this derivative is negative. We said before, the magnetic field in the z direction is decreasing with positive z. So this derivative is negative. So if a particular silver atom has a positive mu sub z, a positive z component of magnetic field, positive times negative is going to be negative. The force in the z direction is going to be negative. That atom is going to experience a downward force and accelerate downward toward the bottom north pole piece. Now, a silver atom with positive magnetic dipole is like a little magnet with its north pole above its south pole. And so what we have is that the south pole of the little dipole magnet is attracted to the triangular north pole of the pole piece, and it's attracted and it accelerates toward the bottom pole piece where there's the greatest attraction of opposite poles. The north pole of the experiment magnet and basically the south pole of the silver atom with a positive magnetic moment. Silver atoms with negative magnetic moment experience an upward force and accelerate towards the top pole piece, the least repulsion of like poles. There's also a force in the x direction proportional to the atom's magnetic moment component in the x direction, because the magnetic field in the x direction is changing in the x direction, and it is the negative of the derivative of the z component in the z direction. This is inescapable because the magnetic field always has zero divergence. That effect cancels out over a short time interval of the atom's travel and does not affect the result. But I don't want to explain this. You can find this in books. This is a possible time to take a break. Okay, a lot of that was confusing. Don't be confused about it. You can ignore a lot of that starting now. We still have to do a little more physicsy stuff, but it will get easier, and then we will get to the result, and then it will be the result that's important, not how we got there. Now, silver atoms all have the same single value of the magnitude of magnetic moment. However, leaving the oven and passing through the collimator, the direction of the magnetic moment could be any direction in space for any single atom. There's no magnetically preferred direction in the oven. Classically, the z component of the magnetic moment and therefore the z component of force, they should be spread across all values from its maximum positive value to its maximum negative value, and the detector should show this classical spread. So the expectation of physicists generally before the experiment was done was the classical expectation that because the magnetic moment orientation is random here and random here, random entering the magnet, individual atoms, the collection of atoms will be spread from here to here on the detector. That would be the classical result. And some physicists advising Stern felt that there was just no reason to test that because that will be the result. Now, but nevertheless, Stern proposed testing it and Gerlach tested it. What is the result? The actual experimental result is that the beam of silver atoms splits into two beams of equal intensity, one with the maximum positive value of a Z component, and one with equal and opposite negative magnetic moment. Definitely not classical behavior. Could not have been predicted. Nothing in the Bohr model or old quantum theory would predict this. The Z component of the magnetic moment of the silver atom is quantized by this experiment. This is the result. One beam goes up, one beam goes down, nothing in the middle. That's pretty interesting. Why would that happen? The magnetic moments in the oven are randomized all over the place. There's nothing special about this Z direction. Why do the atoms do this? How do the atoms do this? That'll be the rest of this lecture. And not with very many formulas from here on out. A few formulas, but not a lot. This is a possible time to take a break. So we understand this result as follows. We've had a little bit of quantum mechanics. The quantum mechanics we had was spatial, but it did involve measurements. So we know that measurement is a interesting and funny thing in quantum mechanics. So an individual neutral silver atom, it's effectively a small magnet. It possesses a small but definite amount of magnetism, called its magnetic dipole moment. This magnetic dipole moment is an intrinsic, built-in, internal quantum mechanical property. At this point, we would say of the silver atom, but we're going to learn in a little bit that it's a quantum mechanical property of individual electrons. We will see that. This quantum mechanical state space for the state is two-dimensional. We got two spots, so the state space is two-dimensional. It's a finite state space. It's not the infinite dimension space that we had for spatial wave functions. So we can select two independent orthogonal basis states and then represent states as a two-element vector, an abstract vector, not a spatial vector, with possibly complex valued components. Silver atoms exiting the oven and passing through the collimator, they can have their magnetic dipole moment point in any random direction in three-dimensional physical space, and we'll be able to represent these states as two-element vectors. We're not going to do that in this lecture. We'll do that in lecture D3. As a silver atom traverses the inhomogeneous magnetic field of the Stern-Gerlach magnets and then gets detected by the detector, the atom's detector position gets measured in the quantum mechanical sense that we used in the C series of lectures on spatial quantum mechanics with Schrödinger equation. And this measurement collapses the state to one of two eigenstates of the Z component of magnetic dipole moment, parallel to or anti-parallel to the magnetic field between the pole pieces. So in the plus Z or minus Z direction. And this state collapse, these one of two eigenstates that will be the state will collapse to, one eigenstate corresponds to the top spot, the other eigenstate corresponds to the bottom spot. The atom's traversal of the experiment remains a quantum mechanical state until its position is finally detected by the detector. Once detected, there's no longer any memory of the prior initial direction of that atom's magnetic dipole moment in the oven or in the collimator, other than that initial direction determines the probability for that specific atom to collapse to either the plus Z eigenstate or the minus Z eigenstate, and so its position at the detector. But initial information gets lost as soon as it gets detected. Now beware, quantization of this magnetic dipole moment was originally called space quantization, because the orientation in space of the magnetic dipole moment of the atoms is quantized. This should say is. And let me change it, because the orientation space in space of the magnetic moment of the atoms is quantized. You may find some book that calls this effect space quantization. I believe the modern view is that the term space quantization is unhelpful to learners, and it's confusing, and it adds nothing to understanding. It might have been better if they, had called it orientation quantization, but they called it space quantization, and that's a bad term. Now we refer to it as spin orientation. The older term space quantization also has nothing to do with the possible quantization of space-time at the very small Planck scale due to presumed quantum gravity. We don't yet have a theory, a testable theory of quantum gravity, but space-time might be quantized in some very, very small scale. This term space quantization has nothing to do with that. It's just an older term. This is a possible time to take a break. Intrinsic spin angular momentum. Well, we talked about the silver atom's magnetic dipole moment, but it turns out we can relate that to an intrinsic property of electrons, intrinsic spin angular momentum, or spin. And we want to do this because spin is more fundamental and more important than magnetic dipole moment. Even though this experiment is magnetic, spin is more important. This experiment helps us to learn that there is spin, but once we know that there is spin, spin is what we want to talk about. From spin, we can address a broader set of cases and phenomena. Courses and books will describe the Stern-Gerlach experiment primarily in terms of spin, both magnetic moment and spin. Spin is the eventual understanding of the result and the takeaway. Magnetism and the magnetic moment gets us there, and then we want to understand spin. We will be able to see why the silver atom reveals this property of the electron. It's not obvious, and if you think it's not obvious, that is correct. Now, if you're a chemist and you're pretty familiar with electron orbitals, you might feel it's obvious, and maybe it is. But to an average person, I don't think it's obvious, and it shouldn't be obvious. And we will break down why the silver atom is a good choice. This is a possible time to take a break. Now, the magnetic dipole moment can arise from a charged particle in a state with non-zero orbital angular momentum, L, and classically orbiting particle like in the Bohr model which is not quantum mechanical, but even in quantum mechanics, there is orbital angular momentum. Some orbitals in an atom, the p orbital, the d orbital, those electrons in those orbitals do have orbital angular momentum, even though we didn't cover it in this introduction. So magnetic dipole moment can arise from a charged particle with non-zero orbital angular momentum, or from a charged elementary or composite particle, or even a neutral composite particle such as the neutron, with non-zero intrinsic spin angular momentum, which we call S. So spin angular momentum is S, orbital angular momentum is L. They're both vectors. Vectors can have will have a component in some direction that we choose, for example, Z. Now, if you want to see how magnetic dipole moment arises from and relates to orbital angular momentum, I'm going to cover this as an optional final section of this lecture, but you don't need it for this lecture and you don't need it for the rest of the lectures. But if you want to see it and you want to see it now, you can jump ahead to that, or you can see it at the end of this lecture. Now, for spin angular momentum, the magnetic dipole moment due to spin, I maybe should have given this a subscript S due to spin, but I didn't, because we're going to be concerned with cases where there's no orbital angular momentum. That's true for the silver atom, and it's important to get the experimental result of two spots. So I probably should have called this mu sub S for spin, but I just called it mu. So the vector magnetic dipole moment is proportional to the intrinsic spin angular momentum, S, and the proportionality is GQ over 2M. In SI units, it's different in CGS units, where there's a factor of the speed of light in the denominator. We're not going to use CGS units. So G is the dimensionless G factor, or G value, or dimensionless magnetic moment specific to that particle. We'll talk more about that. Q is the electric charge of the particle, so minus E for an electron. M is the mass of the particle. Now, we can take the Z component, and that just removes the vector signs and gives a subscript of Z for the Z direction. And it turns out, we know before that angular momentum, the units of angular momentum are the units of H and H bar, Planck's constants. Those have the same units as angular momentum. So we could take the magnetic dipole moment formula, and we can multiply by an H bar in the numerator and H bar in the denominator, and we're going to do that. And the reason is that lets us think then of spin as some number times H bar. H bar has the right units and the right value, the right magnitude, and so we're going to do this. This is a possible time to take a break. Now, it turns out that for electrons, protons, neutrons, and many other particles, but not photons, the Z component of intrinsic spin angular momentum, intrinsic spin angular momentum, can only take on two values. And those two values are plus or minus H bar over 2. It's amazing, but now a little predictable, that here we have yet another case where something in quantum mechanics produces the Planck's constant, the reduced Planck constant, h bar. So if we divide by h bar, Sz over h bar can only take on two values, plus or minus 1/2. Only, ever. It can only have these two values. It can only ever have these two values whenever it gets measured. So whenever we measure the z component of spin for an electron, a proton, a neutron, we will only ever get plus 1/2 or minus 1/2, only ever. That should be surprising and also confusing. And we'll try to address some of the confusion. But we won't fully address the surprising because it's a very weird thing. It's a weird thing about quantum mechanics, and it could not have been predicted. And it's not only a weird thing, it's an important thing in our universe. It's important to chemistry and material properties and crystals and magnetism. These particles with this property are called spin 1/2 particles. And their spin state is two-dimensional, two independent components. Spin only has two values, and an experiment that measures the z component will collapse the state into one of two eigenvalues. And so the spin states are two-dimensional, have two independent components. These spin 1/2 particles are fermions. We've mentioned fermions before in an earlier lecture, and we will talk more about fermions in a later lecture, but not in this lecture. Now, still at this point, we don't really know why silver atoms were a good choice, and I said that the electron has two possible values for the measurement of the z component of spin, but the silver atom has a lot of electrons. Well, why should the silver atom have two spots? The silver atom is not an electron. It's many electrons and many protons and many neutrons. So if you want to say, wait a minute, BS, this doesn't explain anything, you're on the right track. It will explain it, and we'll get there. But if you are skeptical at this point, that's great. This is a possible time to take a break. Now, the dimensionless G factor, or G value, or dimensionless magnetic moment, specific to the electron, it's not predictable from non-relativistic quantum mechanics or the Schrödinger equation. The non-relativistic Schrödinger equation, it's compatible with the existence of electron spin, which is good for us. We can still solve problems with the Schrödinger equation, but it does not predict it. Nothing you can do to make it predict it. Spin gets introduced as a separate postulate. Well, okay, we can live with that, but I mean, that doesn't feel like the end of the story. It turns out spin 1/2 does arise naturally from Dirac's relativistic equation for the electron, which we did not cover, and we're not going to cover. Dirac's equation does give a G factor for the electron as exactly 2. Including spin, electrons in atoms have 4 quantum numbers. You might remember this from chemistry. We covered it very briefly, not adequately. A real course will cover this, but there are quantum numbers for the electrons, the principal quantum number N, the angular momentum quantum number L, the z component of orbital angular momentum M sub L, and now we have a 4th quantum number, the z component of the magnetic moment due to spin. The first 3 quantum numbers, they're for the spatial wave function. We can get those from the Schrödinger equation for the hydrogen atom with no spin. we get those three quantum numbers. And let's notice something here. There's three quantum numbers for the spatial wave function, and there's three dimensions of space, x, y, and z. Okay, that's curious. It means something, but we can't figure out how to get from here to there. But now we've got this fourth quantum number, so that upsets everything, right? Well, no. The fourth quantum number is for the spin state, and there's four dimensions to relativistic space-time, x, y, z, and time. Electron spin is non-classical. It's intimately connected with special relativity, which has the four-dimensional space-time. But we can handle spin correctly without knowing special relativity, without using relativistic quantum mechanics. Now that we know about it, we can use it in Schrodinger's equation, and that's great. So it comes from relativistic quantum mechanics, but we don't have to use relativistic quantum mechanics. That's great. This is a possible time to take a break. Now, it turns out that the more complete and more exacting quantum electrodynamics, quantum field theory, it takes into account the creation, polarization, electrostatic screening, and annihilation of virtual electron-positron pairs from the vacuum, which the Dirac equation does not do. This more exacting theory predicts a G value for the electron of 2.002319, and that has been experimentally confirmed. In fact, if we take quantum electrodynamics' prediction for the magnetic dipole moment of the electron, that agrees with experiments to better than this accuracy. It agrees to 13 significant figures. It's the most successful prediction and experimental confirmation of any scientific theory in science, not just in physics. This is a possible time to take a break. The electron is a structureless point-like particle, but not the proton and neutron. They're composite. They each consist of three quarks and a sea of gluons. The G factor for the proton can be measured, and it is plus 5.586. Now, what about the neutron? The neutron's a funny little guy. It's electrically neutral, but it actually still does have a magnetic dipole moment, because those three quarks are never all at the same point. They're moving around, and they're never sitting at the same point as one another, and so they do give rise to a net magnetism, but not a net electrical charge. So the neutron is not point-like, it's composite. The charged quarks are not occupying the same point in space, they're moving around. There is a G factor for the neutron, minus 3.826, but when we use that, we plug in the charge plus E in the equation. Even though, in other respects, the neutron is has zero net charge. So beware, this is confusing. I find that books will tell you the G factor of the neutron, and then you'll look at that equation and say, but Q is zero. So what? What's going on? So beware of that possible confusion. Now, the G factors for the electron, the proton, and the neutron, they're of the same order of magnitude, but the mass of the proton and neutron are 1,800 times more than the electron. And the mass appeared in the denominator in the magnetic moment equation. Therefore, the magnetic dipole moment from a single unpaired electron is much higher than the contribution from any single proton or neutron in the nucleus. In fact, it's higher than the total contribution from the nucleus, a lot of which gets canceled out. But even if it didn't, a single unpaired electron will dominate the magnetic dipole moment of an atom, as it does in the case of silver. This is a possible time to take a break. Silver atoms have 47 electrons, 47 protons, more than 47 neutrons. We're not going to care about the protons and neutrons because of the discussion we just had, that their magnetic moment is much smaller than a single electron. So we need to know about the electrons in silver. 47 electrons, a chemical valence of +1. They're happy to get rid of one electron in a chemical bond. The electron configuration of silver is noble gas atom krypton, then a full shell, 10 electrons of the 4d orbital, and 1 electron in the 5s orbital. All of the electrons in the krypton noble gas are paired. All the shells are full. The 4d shell is full. All those electrons are paired. So all electrons but one are paired. They're paired with opposite spins. That's what you'll hear that in a chemistry course, but the opposite spins are actually the spin singlet state, which we're going to learn in a future lecture. And they contribute net zero spin angular momentum. So the only spin angular momentum of the silver atom is the one unpaired electron, and then all the protons and neutrons in the nucleus, and we're going to ignore them because their contribution is more than 100 times smaller than one single electron. Electron levels n equal 1, 2, 3, and 4 are all completely filled. Those shells are 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4d. Those are all completely filled. And those completely filled shells contribute zero orbital angular momentum. The 5s orbital, where the one unpaired electron is, it has zero orbital angular momentum. All s orbitals have zero orbital angular momentum. Now in this case, the 5s orbital is half filled. It's the outermost shell that has any electron occupation. 5s, like all s orbitals, has zero orbital angular momentum in quantum mechanics. Now that wasn't true for the Bohr model. The Bohr model said that every electron orbit had orbital angular momentum, but that was one of the things wrong with the Bohr model, and that gets fixed with the Schrödinger equation. So the Stern-Gerlach result shows that the Bohr model's orbital angular momentum values, they're not right for the silver atom. That's not the main result of Stern-Gerlach, but it's a sub-result. This zero orbital angular momentum, that's resolved when the Schrödinger equation was solved for the hydrogen atom in 1926. It could not predict spin, but it would correctly predict that if there was one electron in an s orbital, it had no orbital angular momentum, and so it would not have any magnetic dipole moment due to orbital angular momentum. This is a possible time to take a break. So, as a result of all these things, the neutral silver atom does indeed act like a single electron spin and magnetic dipole moment. but the atom is electrically neutral, so it's not charged, so it won't be deflected according to Lorentz's force law for a charged particle as a standalone electron would be. So the silver atom is behaving like the spin of a single electron without that electron's charge. So the silver atom was a good choice for this experiment. Now, you could have some questions. Why is the electron configuration of silver 4d10 5s1 and not 5s2 4d9? Isn't the 5s shell lower in energy than 4d? The 5s shell is indeed lower in energy than 4d while the 4d is unoccupied. But as we start to occupy it with electrons, the energy levels shift with each added electron. Niobium, with 41 electrons, pulls one of the two 5s electrons into 4d. Now this matters for the choice of silver in the Stern-Gerlach experiment. Silver's unpaired electron is in the 5s orbital, which has zero orbital angular momentum. We want zero orbital angular momentum here so that we see the intrinsic spin angular momentum by itself. Suppose we had used technetium here. I wrote this as 32 electrons, but I think that's wrong. It must be 42. Suppose technetium had been used. Its unpaired electron is in the d orbital, and it would have exhibited orbital angular momentum in addition to its spin angular momentum. And we don't want that. So that would not have been as good a choice as silver. Now you could say, geez, we're putting a lot of guesswork into the silver stuff. Couldn't we have used a simpler case? Silver was convenient in that it condensed on Gerlach's glass detector, and then he could look at it. But in 1927, Phipps and Taylor, they used hydrogen atoms in the Stern-Gerlach experiment. They got the same split into two levels. I don't actually know how they detected the hydrogen. That would be interesting. Their oven temperature was low enough that the atoms were all in the 1s ground state, but they were atoms, not molecules. In the 1s ground state, they have zero orbital angular momentum, and this made it clear that indeed the hydrogen atom with one electron was giving two states. So it is the electron indeed that has the intrinsic spin angular momentum. Now, why did Gerlach use silver specifically? He did also use some other materials. I don't know which, however. I haven't looked up his paper. Group 11, copper and gold, they should have given the same results as silver. Group 1 alkali metals, such as lithium or sodium, those would have avoided the D shell complication, but possibly those might have been too chemically reactive in the oven. Atoms from group 3 through 10 or 13 through 17, they would have had different results, additional spots, because they would have had orbital angular momentum. Now you could say, oh, it's an experiment with a magnet, we should use iron, we should use nickel, that'll give us a good experimental result. They're magnetic. Well, yeah, they're ferromagnetic, but for the same reason why they make good permanent magnets and good soft magnets is why they would be bad in this experiment. They have multiple unpaired electrons, and they also have orbital angular momentum This experimental result would be complicated and messy, definitely not the way to isolate the spin of a single electron. So we don't want to use ferromagnetic atoms in this experiment. This is a possible time to take a break. So it turns out that using silver atoms in the Stern-Gerlach experiment is actually measuring the spin state of a single unpaired electron. The detection at the detector collapses the electron's spin 1/2 spin state to one of the two spin eigenfunctions of the SZ observable Hermitian operator for the z direction, because that is the orientation of the inhomogeneous magnetic field as we've defined it. The experiment measures the atom's magnetic dipole moment's z component, but the experiment has been cleverly arranged so that it's also measuring the unpaired electron's spin state and showing us the quantum mechanical nature of the spin state. We say that the detected atom either had its unpaired electron spin up, or z plus or z up, or spin down, or z minus or z down. The atom's spin state was a spin superposition state until the instant of detection. In this orientation of the magnets, pointed north pole at the bottom, flat south pole at the top, a spin-up electron would be deflected up, a spin-down electron would be deflected down. Because we've arranged that the magnetic field is pointing in the plus z direction, but is decreasing in the plus z direction. This is a possible time to take a break. Spin, spin, spin. So the electron's spinning, right? Is the electron spinning? No way. It's not spinning. Don't think that it's spinning. We're always going to continue to call it spin, but it's not spinning. Nothing's spinning. When intrinsic spin angular momentum was discovered and proposed, physicists first modeled the electron as a uniform sphere of charge spinning on an axis. This gave a G factor of 2, which was great, but when they looked at the result, it required that there be more electrostatic self-energy in the sphere than the electron's rest mass energy, and it required that the surface of the sphere move 10 times faster than the speed of light. Ever since then, physicists have wanted to know, well, what is the size of that electron? So they perform higher and higher energy experiments, smacking electrons into each other, trying to find out its true size. And every experiment so far to try to determine the size of the electron has produced no finite size. It still appears point-like to every physicist's experiment. Intrinsic spin angular momentum is therefore an inherent intrinsic particle property with no valid classical model. Physicists know this now. Even if the electron was discovered in 10 years or 100 years to have some finite size, physicists would not question spin. They understand spin completely now. It's just that the electron is not spinning. We're still going to call it spin, though. Nevertheless, the term spin took hold. It's visually useful, though it's wrong. Just like the Bohr model is visually useful, but it's wrong. Spin persists among all professional physicists and chemists, as well as professors, teachers, and students. But that electron is not spinning. The electron has intrinsic spin angular momentum, and it always does. This is a possible time to take a break. Now, for an electron, we can use the formula that we had before. We can plug in that the charge is minus E. We find out that the magnetic dipole moment of an electron is minus 2.002319 times a constant that we call the Bohr magneton, EH bar over 2 m sub E, in SI units, a factor of speed of light in the denominator for CGS units. And we don't care. We're not doing any experiments, so we're gonna just round this to minus 2 and think of it as minus 2 times the Bohr magneton times S over H bar. And we know that S over H bar is only ever going to have a Z component of plus 1/2 or minus 1/2. Now, not relevant to Stern-Gerlach, but FYI, in different experiments where we care about the magnetism of the proton, we define the nuclear magneton, and that just has the mass of the proton in the denominator. So it's 1,800 times smaller than the Bohr magneton. Now, here's another question that some people might be confused. If G equals 2 for an electron and S sub Z is plus or minus H bar over 2, can't we just multiply across and say the electron has spin plus or minus H? Spin 1. No, don't do that. Spin 1/2 particles have 2 independent spin states, as shown in the Stern-Gerlach experiment. We will later learn that spin 1 particles with non-zero rest mass, speeds less than the speed of light, they have 3 independent spin states. And Stern-Gerlach showed 2 spots, not 3. So the electron is spin 1/2. The photon is a special case in that it has 0 rest mass, it travels at the speed of light, and although as a spin 1 particle it should have 3 spin states, because it's massless it only shows 2, not 3 independent polarization states. But physicists definitely know that electrons are spin 1/2 and photons are spin 1. And in future lectures we will look at each of these individually. Now, the silver atoms coming out of the oven, they're in thermal equilibrium with the oven temperature. They have a spread in their energies, a spread in their velocities. Different atoms will have different velocities. They'll spend different amounts of time traversing the magnets. They'll be deflected slightly differently. The 2 detector spots will have some spread. Gerlach's original experiment used electromagnets, not permanent magnets. So when he shut the electromagnets off, there was a short narrow band in the X direction, not a spot as I've described it. And as he increased the current through the electromagnets, one band separated into 2 bands. I've characterized them as spots for simplicity, but another book may describe them as bands. I was just trying to simplify the explanation. This is a possible time to take a break. Now we're going to change gears. For future lectures, we're going to do some more complicated experiments with Stern-Gerlach, but we're not going to care about the magnet arrangements. We want to just understand it as an abstract machine. And so we're going to conceive an abstract Stern-Gerlach machine, and in fact different machines for different directions. We're going to have an SGZ machine in the Z direction and an SGX machine in the X direction. In lecture D3, we're going to want to explore the quantum mechanics of spin 1/2 states. We want to leverage the Stern-Gerlach experiment and build upon it, but we don't want to think about magnets anymore. Sick of magnets. We want it to be a simple machine with a simple result. We want some simple abstract machines as building blocks. We can build these machines. We can build them with magnets or electromagnets. The machines would give the true physical results. We just want to think about it more abstractly. So we're going to call each of these Stern-Gerlach or SG machines, but other books will call them SG device, SG analyzer, SG apparatus, all same thing. Each machine will have one input port and two output ports. We'll dispense with the oven and the collimator. We're just going to posit an input port where we can inject one neutral silver atom at a time, not a beam, one at a time, straight into the input port. The silver atom's unpaired electron has spin 1/2. Different electrons will use either known or unknown orientation of its spin angular momentum and magnetic dipole moment. There will be two output ports labeled plus and minus. If we put detectors after both ports, then each atom injected into the input port will be detected by exactly one of the two detectors. If the atom is detected at the plus port, then its state has collapsed with its Z component of spin oriented parallel to the magnetic field inside the machine with our configuration of magnets. If the atom is detected at the minus port, then its state has collapsed with its Z component of spin oriented antiparallel to the magnetic field inside the machine with our configuration of magnets. But we're not going to want to care about the magnets anymore. We're going to want to care about plus and minus. This will be more clear after lecture D3, so if this seems frustrating, try not to let it get frustrated. It'll become more clear in lecture D3, but you might have to refer back to here to see what the machines are again. Now, an atom is never going to be lost or absorbed within the machine. It is never detected by both detectors. It will be detected by one detector or the other. However, before a detector is encountered, the atom remains in a quantum mechanical spin state, possibly or generally in a superposition state. We can feed one machine's output port into another machine's input port with no intermediate detector, and the quantum mechanical spin state is preserved within the collection of machines until the atom finally encounters some detector. We never ever do any measurement within a machine, nor do we cheat and sneak a peek inside a machine. So, we add additional magnets within the machine so that the atom exits straight out the output port in the same direction as it entered the input port, straight, not angled. If you remember Stern-Gerlach, when it hit the detector, it was traveling at an angle, but we want to come straight out. So our Stern-Gerlach machine is going to have these extra magnets in it to straighten out the direction so that the atom comes straight out the output port. So one atom goes straight in the input port, and if we had detectors here, we would detect it that it had come straight out the Z plus port or straight out the Z minus port. For this, so this is the SGZ machine because these magnets are oriented in the Z direction, with the direction of travel of the atom being Y. Let's represent this more simply and abstractly from an external perspective. It's a box with an input port and two output ports, one called plus, one called minus. We label the box SGZ because the internal orientation is Z. So if the particle is detected having coming out the plus port, it was in the Z plus state. If it gets detected coming out of the minus port, it was in the Z minus state. Now we could imagine an SGZ machine built for neutrons instead of silver atoms. We would have to use stronger magnets because the magnetic moment is smaller. We're not going to do that, but we could imagine that. We could possibly have some SGZ machine for protons or electrons, but since they have charge, we'd have to design the machine a little differently. We're not going to do that either. What we do want to do, though, is take the internals of the SGZ machine and make another machine permanently oriented with the magnets permanently oriented in the X direction instead of the Z direction. And we're going to call this an SGX machine. One input port, two output ports, a plus port, a minus port. It's SGX. If we detect it coming out of the plus port, it was in the X plus state. If we detect it coming out of the minus port, it was in the X minus state. Now I'm going to show these abstract SG machines in the same flat plane, but remember, physically, SGX is rotated in physical space relative to SGZ. Some courses show you the spatial orientation in a realistic 3D fashion, and that's great. I haven't done that, but I hope you can follow the abstraction here. We could choose to define an SG theta machine that was permanently rotated theta degrees counterclockwise around the y-axis relative, from the z-axis. I don't think we're going to need this for the coming lectures. We could choose to define an SGY machine, but if in an SGY machine the atom can't be traveling in the y-axis, y direction, it would have to travel in the x direction or the z direction. And then we have to describe how we're changing directions of the atom's travel. I don't want to get into that, and I don't think we're going to need to show you an SGY machine, although in future lectures we will talk about atoms that are in the Y plus or Y minus state. My hope is that by the time we get there, you're following the spin story, so we can not have to add extra machines. This is a possible time to take a break. Now it turns out we also want to and need to define another kind of Stern-Gerlach machine, and we're going to call it a modified SG machine, and we'll use the little m SG, and we can define one in the Z direction and in the X direction. It uses additional magnets internally, and what it does is it's going to merge the two internal pads back into a single output port. So it's basically we had a pair of magnets to split into two beams. We have a magnet that reoriented the beams into coming straight out the ports, but now instead of ports we have additional magnets that continue the curving acceleration back toward the original center line, and then we add other magnets that merge them into a single output port. Now you could say, well, why do that? This doesn't do anything. It does do something if we give ourselves the external capability to put in a block to block the bottom path or block the top path. Then it would do something, and it would do something interesting. So when we don't have any blocks in, the output state is the same as the input state, quantum mechanical state, but it does interesting things when we put in a block. This is called the modified SGZ machine. aside from possibly blocking a path, we are never going to observe or measure an internal path. So the atom remains in a quantum mechanical state, and if we haven't measured which path it's in, we don't know which path it's in, as we've covered in a prior lecture. So this is a modified SGZ machine, and when we use it, we will say in words which internal path gets blocked. And likewise, we can define an modified SGX machine. This is a possible time to take a break. The remainder of this lecture is optional. It's not needed to understand this lecture or to understand future lectures, so it's optional. Magnetic dipole moment from orbital angular momentum. Consider an electron, charge -e, in a classical circular orbit at distance r from the z-axis in the xy plane. At constant tangential speed, v, so the period is the circumference of 2 pi r divided by the velocity. We have a circular current loop of current, I, in the opposite direction as the electrons travel because the electron's negatively charged. The current loop has an area, A, of pi r squared. The orbiting electron has angular momentum, r cross p, pointing in the positive z direction, in this case. R cross P, R cross mv would give that angular momentum. The magnitude of angular momentum is rmv. Now the magnetic moment, you might not be so familiar with it, and I'm not a physicist or a physics student. The magnitude of the magnetic moment for a current loop is the magnitude of the current times the area. Well, the current is the charge E divided by the period, and the period was 2 pi r over v, so the current is EV over 2 pi r, and the area is pi r squared. The pi's cancel, one of the r's cancels, so we get ERV over 2. And if we multiply the numerator and denominator by the mass of the electron, we can then pull out RMV out of the numerator, and we get that the magnetic moment is E over 2m times the angular momentum L. The magnetic moment points opposite to the angular momentum because the current is in the opposite direction of the electron's velocity, and we use the right-hand rule for current loops to find the direction of the magnetic dipole moment. So direction for the magnetic dipole moment comes from the direction of the current and the right-hand rule for a current loop, and it's anti-parallel to the angular momentum vector because the electron charge is negative. The ratio of magnetic dipole moment and orbital angular momentum is independent of the size of the orbit, the orbital period, and the electron's velocity. The ratio is E over 2m. Now, for an electron's orbital angular momentum as a vector, the magnetic dipole moment vector is minus E over 2m times the orbital angular momentum vector in SI units. This is true in quantum mechanics as well as classically, but L becomes a vector operator. It's not simply a spatial vector. In earlier spatial lectures, we did not discuss quantization of orbital angular momentum, but there's always an odd number of eigenvalues for the z component of orbital angular momentum unlike the two eigenvalues for the Z component of spin for the spin 1/2 silver atom in the Stern-Gerlach experiment. This is the end of lecture D1.